Hi, what I want to talk about is jet engines and why doesn't the thrust blow out the front of the engine? Like, why doesn't it go both directions? So I I've pondered this a few times in my life, and then I saw a really cool video the other day where some guy made his own jet engine with a glass casing. It was awesome. Yeah. See-through jet engine. This is awesome. Yeah, look, he's running. Built his own jet engine and he's running it. And like he spins it up and stuff. It's fantastic. Anyway, so that got me thinking: how does a jet engine work? Because I mean, I've thought about this a few times. But like, why doesn't stuff go out the front of the engine as well as the back? So then I searched around. I didn't find anything particularly on YouTube that told me about that. I found a bunch of articles on the internet, and you can find things like how does an engine work. So you've got like suck, squeeze, bang, blow. That seems to be pretty standard. That doesn't seem any doubt. And then this is similar. And then there's like different discussions around on stack exchange, right? Like there's aviation stack exchange, and then there's different answers around and here, and also some stuff on Quora too. And it took me a while to kind of piece together bits and pieces until it became more or less clear in my own mind. So I felt that it was, I guess it took me like 4 or 5 hours of searching around. I didn't really find one holistic answer. Actually, I did find one answer which was very good, which was by this guy, Peter Kampf. Yeah, this guy. His answer's really, really good. He's got the same answer twice, like once in physics and once in the aviation. But it is really good. I really like it. Anyway, so yeah, I mean, you can just stop watching and go and read his answer now if you want. But I'm basically going to give my interpretation of all of the things I've seen around the place, whether it's better or worse, but it'll be different, and it's a different synthesis. So here's how I picture things in my head, at least at the start, and this will do for now, right? So this is just like, I'm not saying this is what a jet engine is, but like this is just how I was imagining things, right? So we've got a tube, and in this tube there's some sort of explosion here thing, and let's, for the sake of argument, just imagine we have some high source of high pressure gas that's just going into where the combustion chamber is, and that gas is just trying to go in all directions, right? You know what? I guess I should start with how is a jet engine supposed to work, and then I'll go through what were my concerns with that, like how was I imagining of that, and then what I think explains these concerns away, so that actually the jet engine does. I mean, obviously it works because it works, right? So, all right. So, can I do a new page? All right, there we go. Okay. I'm not sure how this drawing will fit on the screen, so I guess I can draw myself in here. Oops. Can I undo that? And that's going to be me. All right. So here is my understanding of how a jet engine works. So this is kind of the case. So basically at the front, you've got you've got a fan, which is drawing air in. Then you've got a compressor, which is compressing the air. Now in the compressor area, this is actually getting smaller. So you're basically squeezing air into a smaller area, so therefore the pressure gets higher. And actually this goes up to something like, it compresses it 40 times. Right, so this is going up to something like 40 atmospheres, which is a lot, right? Like 1 atmosphere is something like 14 pounds per square inch, right? I mean, I should probably do like a high level overview rather than just going into the details, but there we go. I mean, I haven't planned this. I'm just talking. Yeah, anyway, so 40 atmospheres to PSI I guess it's going to be a lot. So 600 pounds per square inch. And your bicycle tire, if you've got a high pressure bicycle tire, it's about 100, or like one that you haven't inflated much, it's going to be like 30 or 40 like pounds per square inch, right? So this compressor is compressing 40 atmospheres, which is 600 psi. Oops, I'm really shitty at using that. There we go, 600 psi. All right, so you've got fan, compress, then here you've got the combustion chamber. And this is where we inject fuel, and there's going to be a flame constantly burning. All right, and then this combustion chamber creates a ton of gas, which is going to come out this end. And then at the back, we've got like a nozzle, so that then all of this gas is going to come out as thrust. So there's 4 parts to an engine, and thrust is not a part of them, but that's what comes out of the back. The 4 parts, I believe, is the fan to suck in, the compressor, the combustion chamber, and then at the back we've got this turbine. So the idea of this turbine is that it's going to extract power from the thrust that's going out, from these gases that are going out the back. The turbine is going to extract power and use that to power the compressor. And from a practical point of view, basically you've got a shaft that goes the right way through and connects the turbine to the compressor. They're both on the same axle, and when the turbine turns, the compressor turns. If the compressor slows down, the turbine slows down. They're linked together. There's no gears, it's just a rod like this, and at one end you've got the vanes for the turbine, and at the other end you've got the vanes for the compressor. So this just turns really fast. Like if you look at that video I linked to just now, it's super fast. I mean, you can hear how fast it is. It's very impressive how fast. It's impressive how I managed to get that working, actually. Okay. I mean, I feel. Okay, so this is how a jet engine actually works. But the question remains, why doesn't the gas from the combustion engine chamber go out the front of the engine instead of out the back? Right? Like, alright, so here's what I'm imagining in my head. So we've got a tube, and then, right, let's forget about combustion and stuff. Let's just pretend we've got a thing coming. So we've got this tube which is representing the jet, right? This is the front, supposedly, and then this is the back. And then let's pretend we've got a source of high pressure gas coming in, and that gas is coming into like where the combustion chamber is, because that way we don't have to worry about flames and oxygen and stuff like that, right? And it's going out in all directions, right? And then some of it's going to want to go backwards towards the back of the plane to create thrust, and some of it's going to want to go forwards, right? Then we've got the turbine blades, and we've got the compressor blades, and then these are linked together by a rod. So the gas wants to go in both directions. So, like, why should it go backwards and not forwards, right? Or why wouldn't the vanes just stay static, not moving? Or like, if you spin them up first, why don't they just slow down from friction, right? Like, that was what I was wondering, right? So if you know the answer, then I guess you don't need the video. But that's what I'm going to talk about here. Like, why does this gas go backwards and not forwards? Now, if you read these various articles on the internet, like, people will tell you, oh, well, it's just like a car engine, right? You've got these like 3 or 4 parts, and it's just like a car engine. And in a car engine, the piston draws the fuel and air mixture into the chamber, and then it compresses it, and then it ignites it, and it burns, and then it expands and pushes the piston out. And people are like, well, yeah, the jet engine is the same. But the thing is, the jet engine does all of these things at the same time. They're all happening at the same time. Whereas the piston engine, I mean, I can see in my mind, okay, in this bit it's compressing, and then it sparks, and then it expands. So it's like, when it's expanding, it's not trying to get back out of the air, and right, like the bit where the piston's sucking air into the chamber, like there's no flame going at the same time, and then when the flame is going, the air inlet into the chamber, the fuel inlet, that's all blocked off. So that seems much simpler to me. Right, so all right, so here's the conundrum, like why does the gas go backwards, not forwards? And then there'll also be people saying, well, you have to spin the engine up first, so like you can't ignite this until the engine's actually been spinning for a while. So you spin it using like an electric motor or something. Like you can see this when you take off in a plane. If you're sitting near the wing, you can see they draw up with this big machine, like a huge giant battery on wheels, and they'll plug it in, and then the engines will spin up, and then they'll ignite them. And you can see that also in the video I linked to, where this guy made his own little mini jet engine that first he spins it up somehow. I'm not sure, I didn't read the details, but like, you can see he spins it up really fast, and then he ignites it. Yeah, so all right, so it's spinning first, but that doesn't explain like why doesn't you just, yeah, so obviously when it's spinning, it pushes it one way or the other, but like that it why can't it apply like a torque forwards just as much as backwards? And so with friction, that thing is going to slow down. So that's what I want to talk about. So I've kind of thought this through in my mind and come up with a way that I think about this, which I maybe explains this. All right. So I think the easiest way to start to think about this is to split this into two systems. We can have two systems, right, which are not connected together. So in the second system, we've got like some source of high pressure gas coming into the combustion chamber and going out backwards, and then we've got a turbine. All right, so this high pressure gas comes into the turbine, and we can imagine that this high pressure gas is like it's moving very quickly, and it contains it's capable of doing a lot of work. It can be used for many tasks that need power, right? And the power that its ability to do work, a lot of that power that it every second it's generating, it's I guess it's kinetic energy, right? But like there's also some potential energy somehow in the pressure. I'm not sure if you call pressure potential energy, but like somehow this gas contains a lot of energy, and that energy can do work. And one way that those gases can do work is that they can do work on the turbine. So they can transfer energy to the turbine, and then like energy per second is power. So these gases can put power into the turbine. So like maybe the gases coming out the back, maybe they're doing something like 10,000 horsepower. Maybe that's the power that they are outputting, like 10,000 horsepower. And like 4,000 horsepower can go into the turbine, which leaves 6,000 horsepower to go back out the back of the plane, back of the engine. But so that I'm comfortable with that, right? We've got this source of energy / power, which is like this combustion chamber with all these gases coming out. And let's say it's generating 10,000 horsepower, and 4,000 horsepower is being transferred to the turbine. All right. Okay. And then on the other system, we've also got a system which I feel is fairly intuitive to understand, which is the compressor. So the compressor, we've got these spinning blades like fans. Basically, they start off big, and then they gradually get smaller and smaller as the air gets compressed into a smaller and smaller tube. And so that compresses it 40 times. And so there's going to need to be some energy given to that compressor in order for it to keep spinning. And yeah, we can imagine that that's 4,000 horsepower. All right. So far that makes sense. So we've got all this energy coming out the back, like 10,000 horsepower, which makes sense because, we're burning all this fuel, right? And then we've got 4,000 horsepower going to the turbine, and the turbine is then driving the compressor with 4,000 horsepower, so that all works. All right, so then but that doesn't explain why when we link these two together, gas doesn't try to go this way. And I think this is where the answer from what was his name? Let's find his answer. This guy, Peter Kampf, right? I think this answer is pretty good because he talks about the pressure. So what happens is, so we've got our engine here. So this is the front, and this is the back. And then we've got the compressor. And then we've got the combustion. So this is compress. This is combust. And then we've got the turbine. Okay. I mean, then there's a fan in front of that too, right? All right. So then we've got some different graphs. So this is X. It's like the distance from the front of the engine to the back, right? So this is the front of the, like basically this is the front of the fan, and then this is the back of the engine, etc., right? And then we can plot things like temperature. Let me make that a bit. Temperature. All right, so the temperature starts off at like ambient temperature, and then what happens when it goes through the compressor? Does it stay the same? Actually, because you compress it, like think about if you pump up a bicycle tire, the bicycle tire gets hot and the pump gets hot, right? But when we're compressing it here a lot more than we compress a bicycle. So actually, by the time the air is being compressed and gets to the combustion chamber, not only is it at 40 atmospheres, like 600 pounds per square inch, it's also at 600 Celsius. Right? It's pretty hot. Something like 600. It's pretty hot anyway. It's moving about half the speed of sound, and it's 600 Celsius. Gets to the combustion chamber, and now it gets even hotter, of course. So during the combustion chamber, now it goes up to something like 2000 Celsius. And then I believe it's going to gradually cool off as it comes out of the back, but I mean it stays pretty hot. Right, so that's temperature. All right, now, but what I thought was interesting was the pressure. So the pressure obviously goes up in the fan and the compression. At the point, at the end of the compression, when it enters the combustion chamber, that is the highest pressure part, right? In the combustion chamber, the pressure is going down. And then when it gets to the turbine, it goes down more until it gets to ambient. All right. The pressure is the highest at the exit for the compressor, and then it goes down in the combustion chamber. Why does it go down in the combustion chamber? Well, the combustion chamber basically has a very easy route to the outside, which is through the turbine. The turbine is relatively easy for air to flow through. The blade, there's not too many blades, and the angles of the blades are such that the air can just go through the turbine relatively easily. So the air can just go out the back of the turbine super quickly. So the pressure actually goes down. So because the pressure is highest, and then on the other hand, the compressor has a lot of blades, many sets of blades, and compressing it down. So the air exiting the compressor that's the highest pressure, not in the combustion chamber, but just at the entrance to the combustion chamber, and it's a high pressure because of the compressor. And then in the combustion chamber, the pressure's going down. The air in the combustion chamber is going faster and faster. So the air when it goes into the combustion chamber is going about half the speed of sound, and then as it goes through the combustion chamber, it's speeding up. So if we go back to the previous picture, I don't have a picture, but the combustion chamber itself. So the compression, the compressor bit, the tube is getting narrower and narrower to compress the air, but the combustion chamber bit, the tube just stays the same. So basically what happens is the air moves faster and faster as the air is expanding because of the flame. the burning of the fuel makes everything hotter, and the fuel itself is producing more gas. So everything is expanding. And what's happening with that expansion? Well, it's not increasing the pressure. What it's doing is increasing the velocity, like a bullet coming out of a gun or whatever, right? Like these hot gases are moving faster and faster as they go through the combustion chamber. So I guess we should have a graph of velocity, and I haven't actually looked at a graph of velocity, so this might be wrong, but I'm guessing that. So basically the velocity at entry depends on how fast the plane is going. Like if it's on the ground, the velocity is 0. If it's going half the speed of sound, then it's half the speed of sound. And then basically whatever it starts at, it's going to be half the speed of sound once it gets fairly into the compressor. The compressor bit regulates the speed, so it works out about half the speed of sound, no matter how fast the plane is going. And then it stays at basically half the speed of sound, but it's getting more and more compressed, high pressure. Gets to the combustion chamber, now the velocity is going to start increasing. Right, and then I would have to look at Peter's diagram, which we can do after. But I'm going to guess it's gets higher and higher. I guess we can look. Can we look? Yeah, I guess we can look. I guess that counts as fair use. All right, so which of these is velocity? Velocity is, so we got temperature, pressure, velocity. Yeah, so it goes down. It's actually really slow when it enters. Oh, this is still the compressor. Turbine. Oh, no, this is combustion, right? Oh, it's actually really slow when it gets into the combustion, and then it goes up, and then it's kind of high for the rest of the route. So actually it seems like the temperature actually goes down at the start of the combustion chamber, and then it goes up. Sorry, the velocity, yeah. And then it's pretty high out here. All right, so how does this all relate to which direction these hot gases go? Since in the combustion chamber, the pressure is highest at the entry to the chamber and low at the end, then the gases go towards the low pressure, so they go out of the back. They're not going to go forwards, because then they run into the compressor fans, which are busy compressing everything to 40 atmospheres. So it goes backwards. Okay, so that's where it goes backwards. And then it goes backwards. So the turbine blades, there's not too many turbine blades. It's really easy for the gases to go through compared to the compressor. But if it's so easy for the gases to go through the turbine blades, how can we extract the 4,000 horsepower? All right, so this is, I haven't seen mention of this, so this is my own insight, but like probably it's obvious to many people, they just haven't thought to write it down. But like, work is force time, energy. Energy is force times distance. Distance moved. Okay. Like, we're used as humans to thinking of energy as being just the force. Like, imagine if you were holding a car in the air, that would take a lot of effort. But in theoretical, in theoretical terms, holding a car up in the air actually doesn't take energy at all. And like, you can think of why. Well, I mean, you could just stick it on a big brick or a big rock or something, and it's not going to take energy to stay on that rock. So actually, you only need energy to move stuff against a force. And if you move stuff away from the force, then actually the energy is being done to you. All right, so energy is force and distance moved. Power is energy over time. So it's like energy per second. So if something generates 40 joules in 4 seconds, then 40 joules divided by 4 seconds is 40 divided by 4 is 10 watts, I think. All right. So, and then the energy we said is force times distance. So I'm just going to use F as force and D as distance and T all right, and distance over time is just speed, right? So force times speed. All right. Now in our case, the force is basically the pressure, and the speed, well, so the gases going out the back of the plane are going super fast, right? Because of all that expansion and stuff, they're going out super fast. Whereas the gases coming into the plane, not much air has to go into the intake, right? The air going into the intake, actually, I mean, it's a lot, like something like 1.5 tons a second when a plane's taking off, which sounds like a lot, but it's nothing compared to the amount of gases coming out the back. Right, the intake into the plane is relatively small. The gases coming out the back is much more. So the work that the compressor has to do, the power going into the compressor, doesn't have to be very much because we're not taking in very much air. It's not moving very quickly. It's not moving quickly because we don't need much air. Whereas the gases coming out the back are moving very, very quickly. So the energy, the power in those gases coming out the back is extremely high because they're moving so fast. So we only need to extract a tiny portion of the power of the gases coming out the back in order to power the compressor, because the compressor doesn't have to do much work because the air coming into the engine is moving slowly because we don't need very much of it. So basically we've got the air going in and it's slow, and then we've got the thrust coming out the back and it's fast. So we said that the power is the force times the speed, right? And the force is basically the pressure. So like so here it's going really quickly, so higher power. And here it's going slowly because you don't need much air to go in. Like basically you mix a small amount of air with some fuel and it's going to produce a ton of gases because those gases are really hot and because burning the fuel produces lots of gas. So this is going to be low power. So like the compressor blades don't need much power to move a little bit of air inwards. The pressure on those, the pressure that those blades are having to work against is quite high, but it doesn't have to push that air very far because there's not very much of it, therefore the power is low. Whereas in the turbine, the gases are moving very quickly, so the pressures are going to be maybe comparable. Actually, I mean the pressures are lower, as we said, but even though the pressures are lower, because these gases are moving so fast, then we can extract a lot of power. So then that explains why right back at the start when we separated the systems, like we've got 10,000 horsepower in the thrust, we can take out 4,000 horsepower and give that to the compressor. And we can do that because the gases coming out of the back of the engine just moving so quickly, so there's just like a lot of power to give off. And so the air going into the front is going very slowly, so we don't need much power to turn that compressor. So there we go. That's my synthesis of how a jet engine works and why the gas comes out the back of the engine and not the front. And I'll put links to these various articles I found around the place in the description. And obviously you can go off and read those. And you can put comments below on like, are there gaps in what I'm saying, or is there anything that I'm saying that's wrong or doesn't make sense, or do you have any additional insights? Cool. All right, thank you very much.